Hello everyone, in this video we're going to be talking about the acidity of alcohols and phenols, and we're also going to talk about how to deprotonate alcohols, basically what type of a base you could use to deprotonate alcohols and phenol. Just to kind of compare alcohols with water, water has a pKa of 15.7 and roughly alcohol, and if I take an example of maybe ethanol, the pKa of ethanol is 16. So actually water is a little bit acidic than the alcohol, or you can say alcohols are a little bit more basic than water. Let's compare an aromatic alcohol with an aliphatic alcohol. So aromatic alcohols, such as phenol in this case, tends to be more acidic, and the reason is the resonance effect. So the very first thing you always want to do when you're trying to compare the acidity of two compounds is go ahead and draw the conjugate base of both of those compounds. And in this particular case, the conjugate base of this ethanol is going to look something like this. I'm going to go ahead and take out the proton, and this is how the conjugate base is going to look like. I'm going to do the same thing for the second one. So I'll go ahead and take out the proton on the second one, and we'll have the conjugate base for you. Now, what's the difference between those two? And if I go back to the RE effect where you look at the atom, resonance, inductive, and orbital effect, in this particular case, both of those conjugate bases has the oxygen with a negative charge, so atom effect is out of the way. Now you focus on if there is any resonance. So in the first case, there is actually no resonance. That lone pair on the oxygen cannot go anywhere. There's no allylic pi bond anywhere close by. But when I look at this second structure, this lone pair can actually resonate into the ring. So this can go into the ring and this can come out like this. So I'll have multiple resonance structures. So for the sake of time, I'm just going to copy this down here, and I'm just going to go ahead and draw these multiple times, and I'll rearrange those in a minute. So the first structure, when you go ahead and take this out and create a double bond there, I'm going to have a negative charge here. You want to make sure you draw the two-headed arrows for the resonance structure. And then in the second case, when this lone pair goes into this new location, the pi bond break up and comes onto this new location with the negative charge. So I'm going to go ahead and fix the other structure. So you already had a double bond between the carbon and oxygen. You got a new double bond here, and now you got a lone pair right there. So then you can circulate that again. This goes down here, and the pi bond comes up and goes onto this ortho position here. And then I can go ahead and fix this last structure as well. So you already have double bond there. You got a double bond here. You made a new double bond here, and then you got the lone pair here. And when this goes back, it will go back to the very first resonance structure that you have drawn. So just because you have multiple resonance structures, you have this conjugate base is going to be more stable. So more stable conjugate base you can create, the more acidic the acid going to be. And let's go back to the pKa values. The pKa value of ethanol is going to be about 16, and then the pKa of phenol is about 10. So you can clearly see that phenols are indeed more acidic than the aliphatic alcohols, and the reason is the conjugate base is going to be stabilized by multiple resonance structures. In addition to the resonance, sometimes we may see the inductive effect being played into creating more acidic or less acidic alcohols, and this inductive effect more or less stays the same in terms of explanation for other acids as well. If you have an electron withdrawing groups, they are good to make a strong acid, but if you have an electron donating group, they are going to be making acid less acidic because they're going to be decreasing the stability of the conjugate base. Now, let's try to explain that with these examples. So going back to the examples of electron withdrawing groups and electron donating groups, remember all your halogens are going to be electron withdrawing groups, and electron donating groups are like For right now, it's better to know that all the alkyl groups are going to be electron donating groups. You do have some other electron donating groups that you're going to be learning when you start talking about aromatic stuff, such as alcohols and NH2 groups. They are also electron donating groups. But for right now, remember the alkyl here are going to be the electron donating groups, and electron withdrawing groups are going to be the halogens. The nitro group is in another electron withdrawing group, and there are tons of other electron withdrawing groups. But for right now, just know those. And when we talk about aromatics, you will have more of those into play. So let's look at their conjugate bases. So I'm going to just copy this down and draw these conjugate bases here. So all I really got to do is take away the proton on each of those and draw the negative charge. So again, every single conjugate base here is having the oxygen with a negative charge, so there is no atom effect into being played. And then there is no resonance because none of those lone pairs on the oxygen can go anywhere or can resonate. So then you come down to the inductive effect. So you kind of figure out if there is an electron withdrawing group or electron donating group. And I can kind of look at this first one as a reference because you got two carbons, so one and two there. And then I got one, two in the second one, but then I got this fluorine group, and I know fluorine electron withdrawing groups hold the electron density from the oxygen onto itself. And I look at this third one, I got an extra methyl group on this third one. So this methyl group being electron donating in nature, it's actually going to donate in the electron into that oxygen, increasing the electron density on the oxygen. And if that increases the electron density on the conjugate base, it makes it less stable. So this third one is going to be the least stable conjugate base. This second one is going to be the most stable conjugate base because it pulls the electron density out of the oxygen because of the inductive effect. And then the first one is going to be in between. So when I go back, the most stable conjugate base is going to be coming from the most acidic acid. So this second one is going to be the most acidic, and then this third one is going to be the least acidic. So that's how you're going to be looking at the inductive effect. Sometimes, in addition to the inductive effect, especially the electron donating effect, you also look at the solvation effect. Let's look at an example of these two alcohols I have drawn here, and I'm going to go ahead and draw the conjugate bases of these guys. So when I go ahead and draw the conjugate base of these, I'm just going to copy this down here, and I'm going to copy that down as well, and try to draw the conjugate base of that. So take out the proton, and the conjugate base would be having the oxygen with a negative charge. So again, no atom effect, there's no resonance effect. And you could actually talk about the inductive effect because in second case, you have multiple alkyl groups and multiple methyl groups there. So they're all going to be electron donating. And as a result, they're going to be making this second conjugate base that we have drawn less stable. So that's one way of looking at it, that all right, we have multiple electron donating groups, and as a result, this is going to be less stable, making this particular acid less acidic. So this is going to be less acidic right there. In addition to this electron donating effect here, you can also look at the solvation effect. What that really means, once this goes into to make the conjugate base, I'm looking at how this conjugate base is going to be stabilized by your solvent. So since there is less steric hindrance in case of the ethanol or ethoxide, you can say, I can have multiple solvents around it, solvent molecules around it. But I'm going to draw a line here so that you can see the effect there. But when I'm looking at the second one, I don't really have much of room here to put a lot of solvent molecules. So there's going to be few solvent molecules whenever you have this bigger conjugate base, and that means this conjugate base is going to be less stabilized by your solvent. If you have more solvent molecules around it, it will be well stabilized by the solvent, and it's called a solvation effect. Since you have a less of solvation effect in the second case, that makes this conjugate base less stable, and as a result, that acid is going to be less acidic. If you're using any solvent, like you could be using any solvents from alcohols to other stuff, but if you're using water, then this particular solvent effect is called hydration effect. So nothing really changes there, but if you're using water, then you're just going to be calling it hydration effect, but it's very similar to the solvation, or a matter of fact, it's the same as solvation. You just have a special name when you're using water as a solvent. Okay, so keep in mind you can kind of play this particular one with two different ways. You can look at the electron donating effect here, and you can also look at the solvation effect here. Now let's talk about how you're going to be best deprotonating the alcohols. Well, before we go down there, I do want to talk about the pKa of these guys. The pKa of this particular alcohol is about 16, and the pKa of this tert-butyl alcohol is going to be about 18. And why that's less acidic, we already talked about it. Now, how do you really deprotonate alcohols? Let's say I'm going to go ahead and try to deprotonate this ethanol using NaOH. And I'm going to go ahead and draw a two-headed arrows there because I don't know which way the equilibrium is going to be shifted. And then I'll go ahead and draw the conjugate base here. And then I'll go ahead and make water. And then obviously I'm going to take this away. And then you're going to have the spectator there, which is obviously going to be the Na plus. You could be a little bit careless about the spectator there. So I want to look at the acids on both sides. So I got this being the acid, the alcohol, and then I got this water being the conjugate acid on the other side. So this was NaOH was the base, and then this is toxide is going to be the conjugate base. When I look at the pKa's, so pKa of this alcohol is about 16, and then the pKa of water is about 15.7. So there's really not much a difference between the pKa's of those two guys. So that means there is a good chance this reaction is going to have both this reactants and the products almost in equal amount. If not in equal amount, obviously you're going to have more of this alcohol because you have weaker acid on this side. So it's not the best way to deprotonate this particular alcohol because you're not going to be able to deprotonate all of it, and you're going to have in solution both the OH minus and the ethoxide. And both of those are good bases and good nucleophiles, so they could ruin your reactions. So how do I deprotonate it? Well, a better way of deprotonating a particular alcohol, especially these aliphatic alcohols, is use a stronger base. So when I'm using a stronger base, I can use something like sodium metal or potassium metal. As a matter of fact, any of those alkali metals, or even I can use these alkali metal hydrides. I can use NaH, I can use LiH, or I can use FRH, not OH. So any of those alkali metal hydrides can be used to deprotonate these alcohols. Well, if I want to go ahead and make the product here, the product on both of those is going to be the alkoxide. So in this case, it is toxide plus the hydrogen gas. So hydrogen gas just goes away, and that's how this reaction is always going to be shifted to the right side. So that's why I have drawn this arrow going only to the right side. Obviously, when I'm looking at in terms of balancing these equations, I'm going to have to use, especially when I'm using this, let me move this down a little bit. So if I'm using just the metal, I'm gonna have to use 2 moles of that, 2 moles of that. So I end up making ethoxide there, and plus making H2 gas because I would have to use 2 moles there. So the way it works is these metals, they can donate in the electrons. So because those electrons can be donated, you can have these hydrogen atoms combining together to make the hydrogen gas. On the other hand, if I'm looking at the example of maybe just like the NaH, that one is a little bit more simple because NaH provides you the hydride, which is going to be the H minus, and this H minus will grab the proton. So this is going to grab the proton here, and this is going to put the electron density on that oxygen, and that makes the H2. So again, it doesn't really matter. The stoichiometry to some extent is a little bit you don't have to worry about when you're doing these organic stuff. Sometimes you do have to worry about it, but a lot of time you can be a little bit careless about the stoichiometry. But just be careful. You would be needing two equivalents of alcohols and sodium when you're trying to depronate it because you need to make hydrogen gas, and that requires two hydrogen atoms. In addition, if I'm trying to deprotonate the alcohols, phenols rather, the phenols can actually be deprotonated by either hydroxide or even alkoxides, or like, and why that works. So if I want to go ahead and draw the conjugate bases or the reactants there, I'm going to go ahead and take that out, negative there. Plus I got water made, and I'm going to have the spectator Na plus. The pKa of phenol, I know, is going to be about 10. The pKa of water is about 15.7. So you can clearly see there is a big difference in the pKa's, and your equilibrium here is going to be shifted to the right side. Well, we didn't really have that case before. And if you ever wanna wonder like what's gonna be the relative ratios or what's gonna be the KEQ, the equilibrium constant here, you can always do this. You can always do 10 to the power 15.7 minus 10. So I'm looking at roughly 5.7 there to 6. So that's a very high value for the equilibrium constant that tells you this reaction is going to be shifted to the right side. And we didn't really have that option in the previous case because the pKa's were too close and they more or less be both present in the equilibrium. Well, before we go, I want to kind of look at these examples here. I'm going to try to figure out what's going to be the acidic strength, acidic order on this particular one, and this is going to be F here. So let's look at all of those, and it's going to be a better idea if you can pause the session and maybe do this on your own and see if you get this right. Well, the difference I see, there's nothing on A. I got 3 carbons, 1, 2, 3. On the B, I got 1, 2, 3 carbons, but then I got this fluorine that's going to be electron withdrawing group. On C, I got 1, 2, 3, but then I got these electron donating groups on it, and I got electron withdrawing group on the second one. On D, I got 1, 2, 3. I got an electron donating group again, but I got one less electron donating group in D than C, so that's something you want to keep in mind. And then when I'm looking at E, 1, 2, 3, I got a electron withdrawing group. But when I look at the example of B, the electron withdrawing group is closer in case of B than in case of E. So that's something you want to kind of keep in mind. And then this F, I can say 1, 2, 3. Again, I got an electron withdrawing group, but this electron withdrawing group is not as strong as fluorine, something to keep in mind. All right, so my A is actually the reference. I'm going to put that in the middle. So any electron donating group will be making this particular alcohol less acidic. So I got 2 examples with electron donating groups, C and D. And clearly D has 1 electron donating group. So I'm going to say A is going to be more acidic than D because it's got only 1 electron donating group. But then D is going to be more acidic than C because C has more electron donating group. Now let's look at the electron withdrawing groups. So when I'm looking at B, E, and F, in case of B, I got the fluorine, which is the most electronegative element and is closest to the alcohol. So that should be actually the most acidic in that case. So I'm going to go ahead and put the B here, and then followed by between E and F, I got fluorine and chlorine, and they are the same distance away from the alcohol, but I can clearly see that chlorine is less electronegative than the fluorine. So chlorine is actually going to be less acidic than the alcohol with the fluorine. So it's going to be E here, followed by F, and then you have the ADC. Okay, so this is how you're going to be looking at it. Let's look at this next one here. So again, the difference I see here. Okay, in case of C, I can use that as a reference. Let's look at B. This methyl group is going to be your electron donating group. This A, the nitro group, is an electron withdrawing group. And then in D, the fluorine is also an electron withdrawing group. So the question is between the fluorine and nitro, who is a better electron withdrawing group? And it turns out it's actually the nitro. Nitro is a better electron withdrawing group because it can pull in the electron into the nitro group through resonance as well, whereas fluorine pulls in the electron only through the inductive effect. So as a result, A should be the most acidic, followed by D, and then you have C as a reference, and then you got electron donating group that's going to make this even less acidic than the C. So B would be the least acidic out of all those. Well, let's try this last one here. So on this last one, if I go ahead and draw the conjugate bases on both of those, just to kind of see the difference better, I'm going to go ahead and copy this down as well. So got a negative charge here and got a negative charge on this oxygen. So in both cases, it's the oxygen that's getting the negative charge. So atom effect is out of the way. Then look at the resonance. There is no resonance in the first case, but when I'm looking at the second one, this can actually resonate. So since this can resonate, it will make another resonance structure there, making it more acidic there. So this is going to be stabilized by the resonance. So as a result, this is going to be more acidic than the first one. All right, so if you have any questions, feel free to leave any comments in the section below.